Good evening, ladies and gentlemen, and welcome to the Space Telescope Science Institute. I'm your host, Dr. Frank Summers, and it is my pleasure to welcome you for our public lecture series. When you came in, I hope that you are accustomed now to getting pretty pictures either on that table or I got smart, I put them on this side as well. So tonight's pretty picture that we have is the core of the globular cluster Omega Centauri. If that doesn't make any sense to you, turn over. There are a few hundred words to explain it on the back. And if you want to know even more, Tom says he's going to be featuring this in part of his talk tonight. If you didn't get it on your way in, please grab one on the way out. Our talk tonight is On the Trail of the Missing Galaxies, the Oldest Stars in the Neighborhood by Tom Brown. Coming up next month, we have a multi-wavelength view of stellar life and death in the galaxy Messier 83 by Bill Blair, who's from across the street at Johns Hopkins. November 1st, we have the infamous TBA, which means I'm trying to get somebody to talk. I was hoping somebody will come in and do a talk like, make the universe great again, right? Because, of course, this is 1 week before Election Day. It's not election night. Usually in election years, my November talk has to be pushed back a week. Here, it's just fine because election is actually on November 8th. On December 6th, the talk is to be decided upon, but the speaker is Christine Chen, who will be giving, she's given a talk here before. She does wonderful talks. She just hasn't told me what she's going to talk about this time. or one of the campaign surrogates can come give the November 1st talk. I'm sure this is a very coveted audience. Yeah, Maryland is a state that could go either way, right? All right, construction update, and there really is an update this month, okay? It has been closed, this is phase 1, has been closed since spring of 2016. However, next week, phase 2 and phase 3 at the north and south ends of the project will begin on Monday, September 12th, okay? So this is the last public lecture series of this year that you can approach from the north. You'll now have to approach from the south. Let me show you the map. Okay, so you see this blue area here? This is what's currently under construction that will stop being under construction as of next Monday, okay? Then the part in red up here, from our building here up to the north, up to University Parkway, and down here in yellow along Wyman Park Drive, those will be closed from September to December, okay? So next month in October, when you come to the lecture series, you must come via the south gate into Johns Hopkins, come up Wyman Park Drive to get to us here. You cannot approach via University Parkway. This will all be closed through for the rest of this year, okay? If you need to know more about it, here is the website. I don't have a way to memorize that. Just look for the San Martin Project on the Johns Hopkins University website, okay? So next month, north of STSCI will be closed. Approach STSCI from the south. All right? Hopefully, I will see you all here next month and you won't get lost. Our website, if you need to check on things, we have, you can do our Hubble site Go Talks link or just use your favorite search engine, look for Hubble Public Talks, you'll find this. You have a list of the upcoming lectures. You can watch the links to the live online webcasting from both on YouTube and SDSCI webcasting. You can watch our past lectures all the way back to 2005. These wonderful folks have been webcasting it. So there's lots of stuff. And you can sign up for our public lecture series announcements. A couple times a month we send out reminders of what's up and we tell you where the webcasts are posted if you want to see a lecture that you missed. These are the announcements. You can sign up at maillist.stsci.edu. It's easier to go to our webpage. Actually, we've gotten a ton of signups from our webpage, so that's probably the best thing to do. If you would like to have a question, Tom says something absolutely brilliant, you want to ask him another question, send it to publiclecture@stsci.edu. Give us your comments, and yet another way you could even sign up for the announcements. All right. On social media, Hubble has Facebook, 2 Twitter accounts. It's on Google+, it's on Pinterest, and maybe on a couple other places that I don't know about. I myself am on Facebook, Google+, and Twitter. When I have time, I don't do a heck of a lot of social media, but I try to do it a couple times a week. There will not be an observatory tonight. It probably is clear enough, but the person running the observatory technician is out of town at the time, okay? So you will not have an observatory. But for those of you who are new, usually after the lecture, someone from the Maryland Space Grant Observatory comes and will take you across the street to do some observing. They do have a website, md.spacegrant.org. And I believe they do open nights at the telescope mostly every Friday, okay? So check their website to find out when their next observing session is, because unfortunately we won't have it tonight. Okay, now my favorite part of the night, news from the universe for September 2016. Now, everybody knows that August is a slow news month, right? Not this month. Not for astronomy. We had so much that I actually had to cut down. So there's a bunch of cool news that I'm not going to get to tonight, okay? So let me just go through what I do have relatively quickly. My top story, or I guess I should say my top non-story, is from curious to spurious. I am talking about something I noticed on Saturday, August 27th, an interesting SETI candidate in Hercules. This was on I noticed this on social media, and there was a comment that there was a signal in the direction of the star HD 164595, and that star is known to have an extrasolar planet around it, okay? And it came from the Ratan 600 radio telescope in some unpronounceable place in Russia, okay? And so here is the signal that was published, that you can see the pink line is the actual signal, and the green line is a fit for a point source located in the position of HD 164595. So the conclusion of this article was not that, oh my God, we found aliens, but it was rather softly stated, the signal is interesting and merits further scrutiny. However, once the internet gets hold of it, what do we get? We get this. SETI is investigating a possible extraterrestrial signal from deep space. A strong signal that may originate from a sun-like star. Aliens? Sunlight being verified by SETI. Yeah, okay, so, and it got off into all sorts of interesting conversations about extraterrestrial civilizations that have built a Dyson sphere around their star and are capturing all the light from that star, and for some reason then beaming all that energy right back out into space. I'm not sure exactly why you would do that. I got home Monday night and my wife started telling me about an astronomy discovery. My friends on Facebook, my high school friends who I'm friends with on Facebook, they always start to tag me whenever they see something interesting, say, Frank, explain, explain. So I had to kick in, and I put up something a little less glamorous that said something like, a signal worth investigating, but it's probably not aliens. And I wrote about 10 or 12 paragraphs about it on my Facebook page so that I could explain to people, well, you know, here's what's really going on. Meanwhile, the folks who are actually going to follow up this investigation were doing the follow-up. This is the SETI folks here in the United States, and this is their webpage that they put up to talk about this solar system 94 light years away as a possible candidate. Well, they immediately started turning their telescopes onto this star, looking for something, and they had 10 times better sensitivity, and they didn't find anything. So they were pretty doubtful. And then 2 days later, on August 31st, a press release came out from the Russian news agency TASS that said an additional check showed that it was emanating from a Soviet military satellite which had not been entered into any of the catalogs. Now, we look at this and we say, oh, everyone's making a big fuss over nothing. But this is how science is done, okay? Astronomers who find something interesting and don't have enough sensitivity to really check it out tell others about it, and then those go in and check it and see, and they cross-check it. It has to be observed by multiple people using multiple instruments in order for people to really take it seriously. So the science was done right, because they said, look, we're not claiming extraterrestrials here. We're just saying this is interesting. Somebody please follow up. And the follow-up showed you, oh, sorry, it isn't actually interesting, okay? However, in the internet age, we have a moral to go by here. And the moral of the story is scientists must strive not to cry wolf, because that's the job of the internet, okay? All right, our second story, we're going to do some interplanetary mission updates. The first update comes from the Juno mission to Jupiter. And if you were here in July, I told you about the Juno mission inserting itself into orbit around Jupiter, the beginning of the Juno mission, and the fact that it's going to go into this very tight orbit and go very far away, and it's going to sample the full range of the magnetic field. Well, it's on a very long orbit initially, and it just got back for its first pass. So in July 2016, it does the insertion. It's going to do 2 orbits with a 53.5-day period, and then it's going to follow that by 35 orbits with a 14-day period. So on August 27th, it made its first flyby of Jupiter, and this image right here is as it's approaching for its first flyby, okay? And what we're going to get, at least in the visible light images, come from a camera called JunoCam. And JunoCam is not a science camera, all right? I want to lessen your expectations here, because it is an outreach camera. It's just a 2 megapixel. It's like a webcam sitting on the science satellite, okay? It's going to get some cool pictures, but it's not a real science, deep science camera. Most of the science going to be done from Juno is on the atmosphere and the magnetosphere. It's going to have some ultraviolet imaging and some infrared imaging, and it's going to look at the aurora and such. But the visible light images from Juno, they aren't the highlight. They aren't the science goal of the mission. Okay, but it did get some cool pictures, because we have not studied the poles of Jupiter very much. The last time we saw the North Pole of Jupiter was in 1974. Well, now we have these images, okay? So this is Jupiter's North Pole. All right, let me just go back to this one here. You can see that most of Jupiter is this banded structure, okay? That's the stuff we're used to. If we go look at the North Pole, however, you can start to see, especially in this enhanced image, that you've got all sorts of storminess going on in here. You do not have that banded structure, all right? And what's really cool, not just to see the North Pole, but they got this gorgeous picture of Jupiter's South Pole. All right, now can you see the amazing number of storms? And there's still a little bit of bandedness to the structure, but there's a lot more turbulence going on. There's slower speeds down here, okay, in the motion of it. And so you can see that you've got a different pattern on Jupiter at the poles than you do in that standard banded structure that runs around most of the planet. So this is really cool, because we've really not seen the poles of Jupiter, and we will get more of these as the mission continues, okay? But the next pass won't be until October. At that time, they're going to do a burn to go into the 14-day orbit. So Juno has gotten into its serious science mode. All right, it's getting great observations, and we look forward to more cool pictures, but really a lot more serious science about the atmosphere to come. Our second mission update is about Rosetta, the Rosetta mission, and the lander Philae. Now, if you remember, how many of you were coming to the public lecture series back in 2014? Okay? Do you remember November 2014? Because that's when we had a particular event. Now, let me just go through a little bit of this. Okay, so the Rosetta mission, its final goal was to comet 67P Churyumov-Gerasimenko. Okay? Or, just to make it easier, we like to call it Comet Rubber Ducky. Simply because of its shape. Now, so 67P was the target of it, okay? And the Rosetta main orbiter went into orbit around 67P. The Philae lander was released in November 2014 to land on, actually, what would be the head of the duck, okay? and it dropped on down for 7 hours, and when it hit, 2 harpoons were supposed to dig into the ice and hold it on. Well, the harpoons didn't go. So instead, Philae bounced. It bounced a kilometer upward, okay, relatively low gravity. You know, it could jump really high, and actually did a second bounce and settled into an unknown region on the surface of the comet. It was obviously not pointed upward because it couldn't communicate. They got a few pictures from it, but they couldn't keep it alive, and the Philae lander was declared a loss in March of 2016. However, they knew where it was, and the Rosetta mission, main orbiter, kept orbiting around it and actually moved into closer and closer orbits as the mission continued, and they searched for it, and just a few days ago, they found it. Now, can you spot the Philae lander? Those of you who know where it is, yes. It's actually over there, all right? Let me give you the blow up, okay? This is an amazing image, by the way. It's 5 centimeters per pixel, okay? 5 centimeters per pixel. Amazing stuff of the surface of a comet. Here is the Philae lander. They found it, okay? And you can see it's tipped over on its side, so of course it's not going to have good communication with the orbiter, all right? And here is a diagram, annotated diagram, to help you understand it. They're the legs of the lander. Huh? Where's the ice? The whole comet is ice and rock. Yes, but you know, the surface of a comet is generally a sort of a tar-like substance, okay? Because the volatiles have gone away. All right. This comet only gets into about 1.2 astronomical units at its closest approach to the sun, but still the volatiles will go away. If you get inside 3 AU, then the volatiles on the surface will definitely go away. Okay, so it actually, one of the reasons why the Philae lander bounced was at the surface was harder than they expected it to be. Okay, based on previous things, the deep impact, they expected a softer surface. All right, so this is the Philae lander here. Unfortunately, it's unrecoverable. All right. Call Bruce Willis. There you go. All right. So here's what I want to recap for you the Rosetta mission. Okay. It was launched in March of 2004. It had flybys of Earth 3 times. It flew by Mars once. It flew by 2 different asteroids. It arrived at 67P in August. The Philae landing was in November 2014. Rosetta stayed with 67P as it came up, approached the sun, went through perihelion last August, and 2 years later now, all right, it's still with it, and it's moved down to that very close orbit, and the mission is finally going to end this month. On September 30th, they're going to take the main orbiter and have that also land on the comet. Now, I say land in a general sense because, as one blog put it, it'll be more like a soft crash because it doesn't have the kind of landing gear that Philae was built with. So it will effectively crash into 67P at the time and will continue to orbit with 67P for the rest of history. All right, so we can look for some really cool images from the Rosetta mission the end of this month on September 30th, because as this main orbiter gets in close to the comet, it's got a lot more science instruments that it can take all sorts of cool readings and get a lot of interesting science as it comes in for a landing the end of this month. Okay? All right. I had to throw in one Hubble story. I'm sorry, Tom, I'm taking so long, but I had to throw in one Hubble story because the rest of the stuff was from elsewhere. And our final story tonight is Galaxy late bloomers. Okay, so Hubble released these 2 cool images this month of Pisces A and Pisces B, 2 dwarf galaxies. All right, and one of the really cool things was how these galaxies were discovered. So when I say galaxy, you probably think of something like the Whirlpool galaxy, sort of the standard big giant spiral galaxy, okay? But the Whirlpool galaxy is actually bigger than you think, because this is the visible light view. If we go into the radio and search for the hydrogen gas, the Whirlpool galaxy looks like that, There is a lot more hydrogen gas out there that we can see in radio than can be seen in the visible light of stars. So these dwarf galaxies here were actually found by radio searches looking for blobs of hydrogen. It was actually a survey of the Milky Way galaxy looking for hydrogen clouds, and they found 30 to 50 candidates that might actually be external galaxies. They went through and they narrowed them down to the top 10 or 12, and they chose 2 of them that had the highest probability of actually being galaxies. They didn't know, they couldn't see the stars in these galaxies. They could just see there was a blob of hydrogen there. And when they looked with Hubble, they found the 2 dwarf galaxies. And with Hubble being able to resolve the stars and being able to do the stellar populations of it, they were actually able to tell that these dwarf galaxies are late bloomers. They had a burst of star formation only 100 million years ago. All right, now I know 100 million years is really long to you and me, but in terms of the cosmos, that's 13.8 billion years old. 100 million years ago is way late in the universe to have such a burst of star formation. Okay, so these are galaxies that have been hanging out in what we call a void region of the universe. They're very, very slow developers. They're late developers, and only in the last 100 million years have they had a significant amount of star formation. Okay, so by using the radio to then follow up with optical, we can actually find these rare, small galaxies out in the universe. Okay. They're in the direction of Pisces. They're not in the local group. Okay, they're far enough away that they're outside the local group. Okay. All right, we got to get to our featured speaker. All right, let me switch over to his talk. And our speaker tonight is Tom Brown, and I want to thank him for postponing his talk from May so I could bring in Sandy Faber back then. And I know you guys enjoyed her talk. You're definitely going to enjoy Tom. Tom got his degree across the street at Johns Hopkins University. He did a postdoc down in Goddard Space Flight Center, and then he came to work here at Space Telescope. A very Maryland career. Here at Space Telescope, he's done some amazing things. He's worked on the Hubble Space Telescope, he's worked on the James Webb Space Telescope, and he is now the head of the Hubble mission here. And he is famous in astronomy circles for having taken the deepest visible light image ever of a star field in the Andromeda galaxy. We call it the Stellar Deep Field. And it was recently honored by being on the cover of David Bowie's last album. So, a true guy, a true famous guy, ladies and gentlemen, Tom Brown.
All right, thank you, Frank. Thanks for that introduction. Can everyone hear me all right with the microphone? All right, and another thing you got to remind me now and then is I'm both a little hyperactive and I'm from New York, so you got to slow me down now and then if I start going too quickly, okay? So again, as Frank said, I'll be talking today about the missing galaxies in the nearby universe. This is something known as the missing satellite problem that astronomers have been studying for decades, and one way to attack this problem is by looking at the oldest stars in the nearby universe. So this is work I'm doing with the Hubble Space Telescope. It's a program I put together a few years ago. It was about 113 orbits on Hubble, and the team of folks I show here from around the world worked on it with me. I've listed their names. I won't go through them all, but some of them are observers on Hubble, like myself. There's some folks here who had time on the Keck telescope in Hawaii, and then there are also some theorists on this program who study both the evolution of galaxies in time, the evolution of the universe, and the evolution of stars. So it's a good mix of people who use telescopes on the ground in space, and then also theorists. So this is a simulation from Ben Moore at University of Zurich of how the structure of the universe evolves with time on the right-hand side here. So this little number counting down here is redshift, for those of you familiar with it. So this is redshift going into the present. And the beginning of the simulation, I'll back up here when it stops so you can see it again. The beginning of the simulation starts right after the Big Bang. And then the matter in the universe coalesces in this filamentary structure you see here. This is how theorists predict the universe evolved under the paradigm of cold dark matter. And the assumption here is that there's dark matter permeating the universe. It's cold and dark. That's why it's called cold dark matter theory. And you can't see it, but what you do see are the galaxies that form in the filaments along the structure of cold dark matter. So dark matter is the scaffolding upon which galaxies are built. So the dark matter permeates the universe, and then these filaments are where you have large galaxies. So these bright red points here are galaxies like the Milky Way, giant spiral galaxies or giant elliptical galaxies, and then the little tiny dots are satellite galaxies. The cold dark matter theory conforms with a lot of the observable phenomena in the universe, but one thing it strikes out on is it overpredicts the number of tiny little galaxies. So that's a long-standing problem with the cold dark matter theory. So here's a zoom in of an environment like our own Milky Way. This is from my collaborator Jason Tumlinson, who also works here at the Institute. He's a theorist and an observer. And the simulation I'm showing here is about 1 million light years on a side. And so this is the environment around a galaxy like our own Milky Way. And this shows in his simulation here, in Jason's simulation, the expectations for the distribution of dark matter in the nearby universe, the very nearby universe, within 1 million light years. And it might not sound that nearby, but this is roughly the sphere of influence of the Milky Way. So the Milky Way would be sitting here at the center, and we know there's a galaxy there, it's the Milky Way. And then there's all these little clumps of dark matter orbiting the gravitational well of the Milky Way. And there are hundreds of them in this simulation. And when you look at the number of galaxies actually orbiting the Milky Way, there's only a few dozen. So it's off by a large amount. It's grossly off, the number of observed satellite galaxies compared to the predictions of the cold dark matter theory. So this is the missing satellite problem, that cold dark matter says there's lots of little clumps of dark matter out here, and yet we only see a few dozen galaxies. And these clumps of dark matter are the seeds of galaxy formation. So this was a big shock when people started doing censuses of galaxies, comparing them to theory. And so things are off by more than an order of magnitude. So that's it. In a summary, theory predicts more dark matter clumps orbiting the Milky Way than the number of dwarf satellites we actually see. That's the missing satellite problem. So a solution to this was proposed a while back, and it has to do with the reionization of the universe. So this is a cartoon I'm showing here with the Big Bang on the left and the modern era on the right. And time is just progressing from left to right here in this cartoon. And this is the evolution of the universe. So the Big Bang is right here. Right after the Big Bang, there's a short period here called the Dark Ages, where the universe cooled enough to become neutral. So you have hydrogen is neutral. You just have electron orbiting the proton. Things have cooled down, and the stars have not yet come on. And then the first stars and galaxies are born right here, shortly after the Big Bang. And ironically, what happens is when the first stars and galaxies come on, they illuminate everything. That actually snuffs out a lot of star formation all around the universe, because that light comes on. It's a very strong source, ultraviolet light, and it blows out the gas out of a lot of little dark matter clumps and turns off the star formation. That's the theory here. So you have the first stars and galaxies come on. They come on so rapidly, they actually shut off the star formation in a lot of parts of the universe. So this is the era of reionization, when the universe gets ionized from those first stars and galaxies forming. Then after that era is done, galaxies continue to evolve. New stars are born from enriched gas. You've heard this before. We're all made from star stuff. So stars explode. Their material goes out into the interstellar medium. New stars are born from that enriched gas. And time goes on. And here's when the sun would be born at this point in history. And here we are today. So the sun was born about 4.5 billion years ago. Here we are sitting here in the modern universe, and we look back in time. So now we return to Jason's simulation. So this is the dark matter distribution around a galaxy like our Milky Way. And the theory goes, he's highlighted here in green, those are the satellite galaxies that formed lots of stars, and that's why we know about them. So for decades, we've known about these satellite dwarf galaxies. These clumps of dark matter were large enough to accumulate a bunch of gas, have stars form, and then they continued forming stars until the present era. So these little clumps here all continued forming stars to the present day. And this is what we knew about galaxies up until the stuff I'll show you tonight. This is the assumption that's been made about all galaxies, that galaxies are groups of stars built upon dark matter that have a wide range of ages. They have stars born in the early universe, and they have stars continuing to form up until today. I mean, Frank just showed this press release with these galaxies formed stars very recently. So until recently, every single galaxy had not only old stars, but younger stars as well. What's that? Okay, I thought maybe it was me, sorry. I thought I turned off my phone, I was just checking. Okay, so anyway, this is the theoretical prediction for the kinds of galaxies we've known about forever, for decades, orbiting the Milky Way. The problem is here, you see that a lot of these little clumps of dark matter aren't highlighted. They just stay dark. So this is what the theory predicts, that most of these dark matter clumps never form stars, and that's why you don't know they're there. But they are there. It's just clumps of dark matter orbiting the Milky Way. If this is true, here are these red ones I've highlighted. There should be fossil galaxies out there that we didn't know about that are just ancient. and are made from pristine gas in the early universe, form stars, and then were shut off by the reionization of the universe. So these ones are on the cusp. You have the galaxies that kept forming stars because they were big. Then you have these smaller guys that started to form stars in the early universe, and then the lights came on, and it snuffed them out, and they never formed stars again. So these are ones that kind of like a transition between the galaxies that kept forming stars and the ones that never formed stars at all. And then here I'm highlighting both. So in green now, these are the galaxies that continue to form stars. These are the classical satellites we've known about for decades. In red and pink here, these are the galaxies that got snuffed out right after the Big Bang. And then most of these little clumps never formed stars at all. And that's the possible theoretical solution to the missing satellite problem, is that these dark matter clumps are just sitting out there orbiting around. They didn't form enough stars for us to see them. So if this is true, we need to find these fossil galaxies, these ones in red. We've known about these ones in green for a long time, and Frank showed some of those tonight. I'll show you some pictures of other ones. The key here, since we can't see the dark matter clumps without stars, to prove this theory, you got to look at these pink ones and find evidence for fossil galaxies. So that was the goal of the Hubble program we decided to undertake. So if this theory is true, we should have ancient dwarf galaxies besides the bright galaxy we've known about for decades. This is Fornax, one of the brightest satellite galaxies of the Milky Way. It's a group of stars, millions of stars with a very wide range of ages and a wide range of chemistry. So when I talk about chemistry, I'm always talking about relative to the sun. So there's some stars that have just as many chemical abundance as the sun, and we have some stars that are much, much more metal poor than the sun. They have like 1% of the metals the sun has. So wide range in chemistry, wide range in ages, from right after the Big Bang, 13 billion years old, to up to just a few hundred million years old. So this is Fornax, has a wide range of ages. So a big step forward in the missing satellite problem was the Sloan Digital Sky Survey. This was a survey of a wide range of the sky done with a small telescope on the ground in New Mexico. It's done from the ground. This patch of sky is a summation of all the data from the Digital Sky Survey from a paper from Belakurov et al. In 2007. This is tens of degrees across in the sky, and he basically summed up all the data from this scan of the sky. And this scan revealed a lot of structure in the nearby universe that we didn't know about before. And your eye is already probably picking up on some of it, but I'll highlight it here. So in white, I've highlighted 3 streams of tidal debris. So this is the Sagittarius stream along here. This is the Orphan stream over here, and this is the Monoceros ring. These are debris streams from satellite galaxies that fell into the gravitational well of the Milky Way and then got disrupted by the tidal forces. So the galaxy is not really there anymore. It's getting eaten alive by the Milky Way's gravitational well, and it's just strewn across the sky, this stream of stars here. Then they also found a lot of other little satellite galaxies, which I've highlighted here in pink. So these are new galaxies that were too faint to be noticed before, but they're little overdensities of stars. So this went part of the way towards solving the missing satellite problem. So we had a few dozen galaxies, and this found that, well, okay, some of them are being disrupted, which is making them hard to see, these big streams. And then other little ones were too faint to see. These little faint ones are excellent candidates for these fossil galaxies that the theorists predicted. They said, okay, well, we didn't know about these ones before. Maybe these are these ancient fossil galaxies, and there should be a big support for this theory. So these are the ones we decided to target with Hubble. Before I go on to that, this is the Dark Energy Survey. This came out with some results last year. It found 9 new satellite galaxies. This is a projection on the sky of where they found them, highlighted in blue here. Here's where they are in a different projection from 2 different papers that came out last year. So there are a lot of surveys right now from the ground. This is a really active subfield of astronomy where people are banging away, mapping the whole sky, trying to find the missing satellites. But they're not coming up to the hundreds of satellites that theory predicts. They're increasing the number from a few dozen to several more dozen, but they're not coming up to the hundreds, and that's because most of those galaxies are probably dark. They have no stars. They're just clumps of dark matter. But we are finding more and more satellites. So just to put things in perspective, just to give you a sense of scale here, here's a giant spiral galaxy of about 100 billion stars in the upper left. This is like the Milky Way and Andromeda. And down here is New York City. I'm from New York, so this is the comparison I'm going to use. So this is 10 million people, okay, in the city of New York. Typical galaxies that orbit the Milky Way that we've known about for decades are like this here, like Fornax, 10 million stars. You scale down New York City, you're talking about one theater showing The Lion King in New York City. So this is the relative scale here we're talking about. These ultra-faint dwarf galaxies go down even further. So they only have 10,000 stars in them. They're barely a galaxy at all. And now you're talking about one guy in New York, the host of the Jimmy Fallon show. That's how the relative scales here we're talking about. So the giant spiral like Andromeda or the Milky Way, a classical dwarf like Fornax, and these new ultra-faint dwarf galaxies that were only recently discovered. So when you show people, especially astronomers, when I give this talk to professional astronomers in particular, I sometimes get into arguments afterwards where they say, well, why is that even a galaxy if it only has 10,000 stars in it? Because there are star clusters that have many more stars, and that's true. So this is a globular star cluster, like the picture that Frank handed out tonight, like Omega Cen. This one's actually the picture from that Andromeda image I took a while ago. That's a star cluster in Andromeda. It's a globular star cluster of 100,000 stars, and this is an ultra-faint dwarf galaxy with 10,000 stars. So why is this a galaxy? And that's a star cluster. And the reason is because it's dark matter. This is what I was talking about earlier. Globular clusters, as far as we can tell, have little to no dark matter. So if you measure the mass-to-light ratio, which is something astronomers do in these objects, in units of the sun, you get a mass-to-light ratio of about 2, which is consistent with an old population of stars. That means compared to the sun, there's the ratio of mass to light in the sun. These globular clusters have about twice as much mass-to-light ratio. And that's because most of the stars are really faint and dim compared to the sun. Most stars in the universe are really faint and dim compared to the sun. In contrast, these ultra-faint dwarf galaxies have a lot of dark matter, again, because dark matter is the scaffolding upon which galaxies are built. So galaxies have significant dark matter. The classical dwarf galaxies we've known about for decades have mass-to-light ratios exceeding 10. And the ultra-faint dwarf galaxies have mass-to-light ratios exceeding 100. So these new galaxies are almost entirely dark matter. There's just a big clump of dark matter there with a few stars sprinkled on top, which is consistent with this theory that the theorists used to predict the solution to the missing satellite problem is that you had the dark matter there, a few stars formed, and then things were turned off. The lights were turned off when the most of the universe came on with star formation. Another big difference is that globular clusters are usually what we call simple stellar populations. All the stars, to first order, are just one age and one chemical composition. You have a cloud out there in space. It collapses, and you form a bunch of stars. They all have one age, one chemical composition. Galaxies have a wide range in ages and a wide range of chemical composition. That's true of every galaxy that we've known about until the ones I'll show you tonight. So this is a plot now of, just to put these things into perspective, this is luminosities here relative to the sun. So 10 to the 6 is 1,000,000 times the luminosity of the sun. This is diameter in light years, from 1 to 1,000. So star clusters fall over here. These are globular clusters. They have up to 1,000,000 times the luminosity of the sun, or maybe even 1,000 times the luminosity of the sun, but they're pretty compact. They're on the left-hand side of this diagram. The classical dwarf galaxies are shown here in blue, so they're much more extended, and they're generally brighter than star clusters. They're up and to the right. These ultra-faint dwarf galaxies are down here. They're an extension of these dwarf galaxies to fainter luminosities and smaller sizes, but they're not as compact as globular clusters. So they're mostly dark matter, and they're these wispy things with just a few stars in them. And so we decided to look at these 6 very closely with Hubble, because Hubble is excellent in measuring the ages of stars to test these theories. So how do we know if a group of stars is old? Well, there's 2 ways you can go about it. One is to get spectra of these stars. You take the light from the stars, you spread it out into its rainbow, and then you look for features in that spectrum to see what kind of metal abundances there are. And so if we want to see if it's old, it should have a low abundance of metals. If it was born in the early universe before there were many generations of stars, the gas should be pretty pristine, and so there shouldn't be a very high chemical composition in these stars. We also do photometry. We measure the brightnesses and colors of the stars, and when we do that, we can see what masses are left. Only low mass stars, less massive than the sun, should be present if it's old, because massive stars, more massive than the sun, die very quickly. So these are the 2 tests we do to see if these things are actually old galaxies. So here's a spectrum for an ultra-faint dwarf galaxy, and it tells us a couple different things. So it gets broken into its constituent light from blue, green, to red, and these little dark patches in there are absorption features from metals in the atmosphere of the star. So by measuring the velocities from the Doppler effect of these absorption features, we can measure the motions of these stars, and the motions of the stars in the ultra-faint dwarf galaxies imply there's a lot of dark matter there. So the matter in these galaxies, the luminous matter, is feeling the presence of the gravity from the dark matter. The absorption features, these little patches here, are also very weak. So it means these stars have 100 to 10,000 times fewer metals than the sun. So these stars were really born in the early universe when the gas was still pretty pristine. And this is also a little cottage industry in astronomy. A lot of people are looking for the first stars and the earliest stars and the oldest stars. And folks who are looking for the most metal-poor stars have found a lot of them in these ultra-faint dwarf galaxies. So this is fertile ground for these searches. So this is the same handout you have tonight, this Omega Cen. So it's fortunate that Frank handed this out. I'm going to sort, this is an image from Hubble with the Wide Field Camera 3. This is a camera I worked on before I switched over to James Webb for a while. I'm going to sort this. This is from my colleague, Jay Anderson. I'm going to sort this in color first, from left to right. So hotter stars that are blue will be on the left. Cooler stars that are red will be on the right. Then we're going to sort it in luminosity with brighter stars at the top, fainter stars at the bottom. When you do that, you see that stars don't just have random colors and random brightnesses. They actually trace out a very specific pattern. My wife calls this the duck diagram because it reminds her of a duck. But anyway, here's the body, here's the neck, here's the beak. But main sequence stars like the sun that are burning hydrogen fall down here. And then after they exhaust their hydrogen, they go up here and become red giant stars. And then they finally burn helium, and they become this thing called horizontal branch stars because this distribution is horizontal. So they burn helium, and then they die as white dwarfs. So when you sort a population of stars by brightness and color, they're not random. They trace out a very specific pattern. That's the life cycle of a star. And that's how we can use that information to tell how old a group of stars is. So that's where those stars now fall in that image of omega Cen, which is on the handout over here. So here's measurements of a galaxy. This is brightness again on the y-axis here in these funny units astronomers use. So this is in a filter 814, so 800 nanometer filter. The 606 minus 814, 600 nanometer minus 800 nanometer filter. So this is a color with redder stars on the right, bluer stars on the left, brighter stars at the top, fainter stars at the bottom. Hydrogen burning stars fall along here. Here's this kink, and then they exhaust hydrogen in the core, and then you become a red giant star. And that's how you measure the age of a population. So these are low mass hydrogen burning stars, more massive hydrogen burning stars, and then they peel off and become red giants. So these are stars that are still burning hydrogen in the core. And these are stars that have exhausted hydrogen in the core and become giants. So that's the clock. That little kink right there tells you that's the best clock in astronomy right now. There's a lot of different ways to measure the ages of stars, but that's the gold standard since Alan Sandage started doing this in the 50s. So this is what you'd get for a population that's 13 billion years old, an ancient population. And that's what it would look like for a population that's 6 billion years old. And that's what it is for 13 billion years old. It's a very dramatic difference. And the reason why is because the massive stars die more quickly than the less massive stars. Ironically, if you're a massive star, you have a lot of fuel, but you're very bright and you burn it very quickly. So you leave the main sequence and you become a giant more rapidly than these stars down here. So here's the Carina classical dwarf galaxy. This is out in the local group. Again, a pretty massive dwarf galaxy we've known about for decades. And here's its color magnitude diagram. So this is brightness on the y-axis, color on the x-axis. And you get these three distinct little shapes here. Each of those is from a burst of star formation. If I put models on top of that, this is where stars about 500 million years old would lie in this brighter curve here. Stars 5 billion years old would lie along this intermediate curve here. And really old stars, 11 billion years old, would lie here. So this is a kind of curious galaxy. You don't usually see these episodes of star formation, but in this one you did, and it makes it kind of interesting to show the clock in 3 different places, 1, 2, 3. And this is similar to the stories we've seen for a lot of dwarf galaxies. There's a wide range of ages. You don't see just old stars, you don't just see young stars, you usually see a wide range of ages. So here's the ones we decided to look at again tonight, the ultrafaint dwarfs. And again, I looked at these with Hubble. They're kind of a sample of about 6 galaxies out of the recently discovered ones from Sloan. And this is what it looks like when Hubble looks at one of these. So in the background here, I'm showing a digital sky survey image. And then Hubble has a pretty small field of view compared to some of these ground telescopes. So the footprint from Hubble, from its advanced camera for surveys, is one of these blue tiles here. We kind of went and tiled that part of the galaxy. We turned on wide field camera 3 in pink here in parallel. It kind of missed the galaxy here, so it was just getting a sample of some of the stars in the background. This is about 200 arc seconds on a side. This is Leo 4. So this galaxy is further out from the Milky Way, so it's a little more compact in the sky. So if you look carefully, you can see there's an overdensity of stars right here compared to the background. And so we stuck ACS, the advanced camera for surveys, right here. We stuck wide field camera 3 out here. It got pretty much nothing. But this one measured the galaxy. And so that's the image we got of Leo 4 in that patch. That's this patch of sky right here. This is the Hubble image. It's about 16 orbits. We hand out time on Hubble in units of orbits. Hubble goes around the Earth every 96 minutes. That's the currency on Hubble. So people ask for 5 orbits, 10 orbits, 100 orbits. This was 16 orbits on this one galaxy. We looked at 6 galaxies in total. It's a fairly deep image. Like a lot of images with Hubble, when you're trying to go deep, you get the rest of the universe in the background. So there's all these really pretty galaxies in the background. And a lot of people like those because the stars are just points that are kind of boring. But for me, it's wasted real estate because every one of these patches is where I can't make measurements of the stars. So people like these galaxies. They're just kind of irritating to me. But I'll zoom in on a patch here. So here's this yellow box that I'm going to zoom in. So again, you have these nice, beautiful galaxies in the background, which I just mask out and throw away. And then you have these points, which are stars in Leo 4. And I'm going to highlight 2 of them. These are the most massive hydrogen-burning stars in Leo 4. So these tell you the clock. So when you get measurements of the brightnesses and colors of these stars that tells you how old the galaxy is. So these are the brightest hydrogen-burning stars in Leo 4. So here's the image again, and what I'm going to do now is highlight the stars in this image and show you how they tell us the clock for the galaxy. So these are the stars in Leo 4. And if I sort them in color and luminosity, that's where they fall, at an age of around 13 billion years. And now I can use theory of stellar evolution to roll back the clock here. So now I'm taking the data and just morphing it backwards in time towards the Big Bang. So now this is what the data would look like if we made that measurement a billion years after the galaxy was born. So there's brightness over here, color over here. And now the clock's rolling forwards to the present era. So 5 billion years, 6 billion years, and here's the clock is right here, this kink. This tells you how old the population of stars is. Until you get to the galaxy being about 13 billion years old today, and those are the points, and this is where they fall in that image. So these are the data we got. So we got 6 of these duck diagrams, like I said, these color magnitude diagrams, and my wife calls them duck diagrams. And the first one we got was here. And now here's full disclosure. I'm an observer. I have a team of folks on here. Some work on Hubble, like me. Some work on Keck. I have some theorists on the team. And I'm used to theorists, not to be disparaging of theorists, coming up with a theory, and then you go test, and you go, well, let me revise that theory. So we got these data right here, and because I work on these kind of diagrams a lot, I immediately saw in my office that this was a very ancient population, which is not what I was expecting. I wrote this proposal to measure how old these stars were, and I was sure, just like every galaxy we've ever measured before, there would be young stars and old stars. But instead, the stars were all just old. And I almost fell out of my chair. I mean, you're looking at these and going, okay, it's a bunch of yellow dots. But for me, it was really surprising because I did not expect the theory to be true. And so I called up Jason Tomlinson, who made that simulation in the beginning of my talk, dragged him down to my office. He works one floor up from me here in this building. And he said, well, yeah, that's what it's supposed to do. They're supposed to be old. And I said, yeah, but I didn't think that was really going to happen. I thought there was going to be young stars and old stars, just like every galaxy we've ever looked at before. So those were the first data that executed in the program, Hercules, satellite of the Milky Way. And then we got the other 5 galaxies. And they're all in different positions in each of these diagrams here because some are closer, some are further, so it makes the stars brighter and fainter. But if you do this kind of work, you look at each of these and you say, oh my God, the stars are really ancient in every one of these galaxies. And they also look very similar. These diagrams all look very similar to each other. So just for a comparison, without using any theory, I'm going to take data from another well-studied object that we use to make comparisons to data like I just showed you. This is M92, NGC 6341. It's one of the most well-studied ancient objects in the universe. It's a metal poor star cluster. Alan Sandage looked at this in the 1950s to figure out how stars evolve. It's an ancient star cluster. Its chemical abundances are such that the metals in the atmosphere are less than 1% of the abundance in the sun. It's a globular cluster. This is a half-second exposure on Hubble. Now, Alan Sandage would spend nights on the telescope in the ground looking at this. With Hubble so powerful, this is just a half-second exposure. This is the advanced camera for surveys. It's kind of like your the CCD chip on here is kind of like your chip on your digital camera now. There's a crack down the middle here, splits the chip into 2 halves. So that's why you see these 2 sections here. But it's a 4K by 4K image, a 16 megapixel camera basically on Hubble. And all these are stars in this globular cluster, M92. This is the color magnitude diagram from those data. So this is the luminosity here, bright stars at the top. Here's the color, red stars on the right. And again, stars don't just have random colors and brightnesses. They trace out this very specific pattern. That's the life cycle of a star. Hydrogen-burning stars, they exhaust hydrogen, go up here, become red giants. They come over here and burn helium. And this is the kink right here. It tells you the age. So what I can do is I can just draw a curve through that and say, all right, I'll highlight the helium-burning stars over here, and then I'll draw a curve through this. And now I'll just compare that to the data I got on those galaxies. This is an ancient star cluster, 13 billion years old. It's been studied for 60 years. So here are the data on the new galaxies that we found. And here's where the M92 data fall when you superimpose them at the same distance. It goes right through the data in every case. And really, this was, I don't know how shocking it is to you, but I was flabbergasted when we did this, that all these galaxies, which, like I said, galaxies by definition usually have a wide range in age. Every single one of them looks like M92. So not only are they all old, they all look exactly like each other to first order, at least by eye. So this was kind of astonishing, but it's a pretty good support for this theory of what's happening at the missing satellites. We've known about these galaxies for decades that form a wide range of stars or a wide range of ages, but the theory of the missing satellites, why we don't find them is that most of them never form stars at all. And between those 2 categories, the ones that have been forming stars forever and the ones that never form stars at all, should be this transition group of galaxies that just formed old stars and then were snuffed out in the early universe. And that's what this is telling us. These galaxies formed stars right around the same time M92 was formed and then were snuffed out when the lights came on. These are pretty boring data, but I'll just show them. These are the Keck data we got. So this is number of stars versus the chemical composition. So for stars here, this is 1% of the stellar composition. This is 0.1%. This is 0.01%. So these are very low metallicities compared to the sun. And this is number of stars in the galaxy compared to what fraction of the solar composition there is. So most of the stars fall between 0.1% and 10% of the solar composition. So the stars are very metal poor. They have very few metals. So they're born from pristine gas in the early universe. So this is, again, supporting evidence that these are pristine ancient galaxies. M92, just for comparison, is right here where the green line is. So M92 is a little less than 1% the composition of the sun. It's also ancient and metal poor. So just for another way to compare these data, these are the data from Hercules. I'm zooming in here now on the clock. So the little kink right here, again, this is brightness versus color. And I'm going to take the data from all the other galaxies and superimpose them on here, just to show how similar they are. So this is Hercules in yellow. That's Leo 4 in green. And if you say, well, I can't really see it there, well, it's because they're right on top of each other. That's CVN2 in purple. That's Ursa Major 1 in blue. That's Bootes 1 in red. And that's Colbert in brown. So if you put all these galaxies in the same reference frame, their data fall right on top of each other. These are 6 satellite galaxies of the Milky Way, all at different distances from the Milky Way, all different parts of the sky, and they all look exactly the same to the eye. So that implies some kind of global influence affected all of them. And there's a lot of things going on with galaxies form. Supernova blow off all the gas out of the stars, new generations of stars are born. It's a chaotic process. But something synchronized the star formation in all 6 of these galaxies to a very high degree. And one possible thing that's obvious here after you've heard the pitch in the beginning is that it was reionization of the universe. That would be a global influence that affected all the galaxies. This is where theory tells us the stars should fall if all the stars were between 12 and 13 billion years old. They would fall along this gray curve here, which is a good match to the data. The data spread out a little bit more down here because they're a little noisier as you go faint, but this is where the stars would have been born, right along this curve. So just to show you now a little more quantitatively, this is the zoom in now on the clock for Hercules and the theoretical prediction, a random draw on the theoretical prediction of where the star should fall. So one of these panels is the data, one is the model. I won't make you guess which one is which, but you can see the model and the data look very similar. The green curve is M92 again, just for comparison. So that's Hercules. One's data, one's the model. That's all 6 of the galaxies. So in one panel, I'm showing you the theoretical prediction for how the stars should be scattered around a diagram like this, and the other one's the real data from Hubble. And each panel here, they look very similar, right? The distribution of stars is very similar in each case. And so what it is in each case is the model's on the right and the data are on the left. And the theoretical prediction for where the stars should fall in this diagram matches the data very well. I can show it this way too. The gray shading here is where the theory says the stars should fall, and the yellow points are where the stars do fall. And there's excellent agreement in all 6 galaxies. So this really tells us that these are fossil galaxies. Now, it may not be true that the reionization of the universe is what made them old, but we were testing that theory. We said if there are ancient fossil galaxies, these would be excellent candidates for being fossil galaxies. We looked at them closely with Hubble, and they do seem like they're very pristine in their metallicity, and they're very, very old. They're about 13 billion years old. The average age in each of these fits here, this is 13.3 billion years old, 13.6 billion years old. This is 13.9 billion years old. And I know some of you are going to go, wait a minute, Frank a little while ago was talking about the universe is only 13.8 billion years old. There's about 500 million years of uncertainty in these fits due to the models. So it's consistent with the age of the universe. It's not like we're saying this galaxy is older than the universe. But within the uncertainties, these galaxies were all born right after the Big Bang. This one's 13.1 billion years old, 13.1 billion years old, 12.7 billion years old on average. So these are the oldest known galaxies, these 6. These are the only galaxies where we've measured ages to this accuracy, and all of them are older than any galaxy we've ever measured before. This is another way of showing the same thing. This is the fraction of stars born in the galaxy versus time on the x-axis. So what happens here, so this is looking back in time to the early universe, 14 billion years ago or so, and star formation starts very quickly. 80% of the stars are formed in the very first billion years, and then it kind of tapers off. And the width here is just the uncertainty in the model. So this would be a narrow curve if our models were better. But so the star formation comes on very suddenly, and then there's a little tail as reionization starts to shut things down in these galaxies. So this is a fit to the data for Hercules. This is what it looks like for all 6 galaxies. The star formation, they all look very similar. Star formation comes on very rapidly. 80% of the stars are formed right after the Big Bang, and then there's a little tail going on for a few billion years afterwards as the reionization of the universe shuts off the galaxies and their stars. So Unfortunately for where we live, or maybe fortunately, maybe it wouldn't be such a great place to live, we live in kind of a cosmological backwater. There's not a lot going on in the local group. So this is a box here showing us part of the local universe, 80 million light years on the side. And the kind of work I'm talking about here, where you can use Hubble to measure ages of stars very, very accurately. There are a lot of ways to measure stellar ages that you could do less accurately, you could do them far away. But for doing really accurate ages, you can only do it relatively nearby. And Hubble can do this kind of work in this yellow sphere right here. So that's where we can do the kind of work I'm talking about right now. And it's not a really interesting patch of the universe where we live, unfortunately. So the symbols here, these paperclip looking things that I drew here as my lame attempt to make a spiral galaxy, these are giant spiral galaxies. The Milky Way is right here at the center. Andromeda is our only other nearby giant spiral. These big red things are elliptical galaxies, giant elliptical galaxies, and the little brown dots are dwarf galaxies, like I've been talking about tonight. So we live in kind of a boring part of the universe. It's out in the boonies. There's not a lot going on here. It's the Milky Way, Andromeda, and a few dozen dwarf galaxies, and Hubble can measure the ages of these galaxies. The James Webb Space Telescope is launching in 2018. It could do the kind of work I'm talking about tonight in a volume 3 times larger, so it gets a lot more dwarf galaxies. It starts to get to the spiral galaxy. That's not what it was built for, though. It looks in the infrared. It's got a much bigger mirror. It's going to measure the ages of galaxies by looking directly back in time at high redshift. So if you look very far away, you're looking in time. So James Webb is going to look at the most distant galaxies and observe them evolving directly. It's not going to do the kind of stuff I'm talking about tonight primarily, but it will do some of that kind of work, and it could do it a little better than Hubble. Folks are also looking at building much bigger versions of Hubble. So this is an active thing going on right now. There's a lot of folks looking to see what are the next big NASA missions in the next couple decades. And people are talking about building a UV optical telescope like Hubble that would have an 8-meter mirror. So Hubble's got a 2.4-meter mirror. People are looking at an 8-meter mirror. That would get out of our little, middle of nowhere patch of the universe. You could start doing this kind of work in spiral galaxies, out in the nearest towns. You can actually pick up an elliptical galaxy and lots of other types of galaxies. There are folks who are really ambitious who are talking about building a 16-meter version of Hubble. And this is really stuff that people are looking at right now. The primary motivation for this is to look for life around other stars. So this is the kind of telescope you need if you want to be able to detect life directly on planets orbiting other stars. And if you're going to build such a telescope, people can use it for other stuff too. And people like me, looking for life around other stars is obviously very exciting. I measure the ages of stars. You could do what I'm talking about tonight in this volume of the universe. And that would be a true census of the local universe. You get lots of giant elliptical galaxies, these red things. You get tons of spiral galaxies, many more hundreds of dwarf galaxies. You could really get a census of how the universe has formed its stars in the nearby universe with that kind of telescope. I probably would not get a gigantic fraction of the time. Most of the time it would be looking for life around other stars, but you could get some time doing this type of work. So this is the Hubble Space Telescope in low Earth orbit. So most of the work I've been talking about tonight comes from Hubble, also comes from Keck. I worked previously up until a few months ago on the James Webb Space Telescope for the last 8 years. So I'll just give you a little update on that. This is James Webb. It has, unlike a 2.4-meter mirror, it has a 6.5-meter mirror coated in gold. It's a beryllium mirror. And then just to give you a sense of scale, this is the light shield. This is the sun shield. It's about the size of a tennis court and made of a material similar to like candy wrappers. It's got 5 layers here. It keeps the instruments in the telescope in the shade while it's orbiting out around the sun. We're launching that in October 2018. These are the main science goals of James Webb. So it's going to look at the first galaxies in the universe. So again, it'll be measuring the evolution of galaxies, but in a very different way. It's going to look directly back in time at the most distant galaxies. It's going to watch over that cosmic time how galaxies evolve. Of course, it's looking in the infrared. It can peer through dust and gas to see stars and planets being born. And it's going to be able to look for the origin of life. So these are the main science themes of James Webb. Just for comparison, Hubble is in low Earth orbit. On this scale, you wouldn't even be able to see how far away from Earth it is. It'd be orbiting right there. James Webb's going to go out here to a point we call Lagrange 2. It's 4 times further away than the moon, 1.5 kilometers away. And then just here's a comparison of the telescope sizes. Here is a person, 1.75 meters tall. Here's Hubble's meter, 2.4 meters tall. And here's James Webb, 6.5 meters tall in 18 segments. That's ground testing down at NASA of some of the mirror segments, again, coated in gold. People freak out a little bit when you say the mirrors are made of gold. They go, oh my God, NASA's wasting so much money. The whole mirror has about this much gold on the coating of it, okay? So just for comparison. So it's a very thin layer on the surface. Here are the instruments. So we were testing the instruments individually at different locations around the world up until a few years ago, and then we started integrating them into the Integrated Science Instrument Module. That got tested last year at Goddard. So it's NIRCam, which is a near-infrared camera, MIRI, which is a mid-infrared instrument, also a camera and a spectrograph, NIRSpec, a near-infrared spectrograph, and NIRIS, also a near-infrared camera and spectrograph, specifically designed for exoplanet searches. And here's the test chamber at Goddard, where we were just testing. We wrapped up testing of the instruments this last year in February. This is the chamber that will be used to test the instruments and the mirror together next year in April. This is the same chamber that was used for the Apollo lunar module. I walked around inside this a few years ago before they started cleaning it out and for the testing. I have to say, it's crazy impressive. I mean, those are people standing here. So you walk around inside this scaffolding. It's the same chamber that was used to test the Apollo missions. And it's at Johnson Space Center. We'll be starting testing there next year. And that's what it'll look like. So James Webb will be what we call the cup-up configuration. So the mirror is facing up, and the instruments are sitting here facing down, and we'll do some simulations of the conditions in space to test it before we launch it. So just to summarize, the ultra-faint dwarf galaxies are extremely metal poor. Some of the most metal poor stars in the universe that we know about are found in these ultra-faint dwarf galaxies, and their chemical abundances in most of the stars are 1/10% to 1% of those we find in the sun. The ultra-faint dwarf galaxies are ancient. 3/4 of the stars formed their star. 3/4 of the stars were formed more than 13 billion years ago. So these galaxies are truly ancient. There are none, as far as we can tell, intermediate age stars, so nothing really younger than 10 billion years old in these stars. And that's very distinct from pretty much not only the classical dwarf galaxies, every other galaxy that has ever been studied. Most galaxies have young stars and old stars. Star formation appears to be synchronized in these objects. Even though there's 6 different galaxies spread out on the sky, they all have pretty much the same star formation history. It's like a guillotine came along and shut off the star formation in all of these at the same time. And that's what you would expect if they were all snuffed out by the reionization of the universe shortly after the Big Bang. And this is consistent with solutions that have been posed to the missing satellite problem. Most of the missing satellites are there, but they just have few or no stars, so we can't see them. Thanks, and I'll show this video of the JWST deployment in 2 years while I answer questions. Thanks.
All right, we have all, I'm sure we have lots of questions.
Sure.
This is my first time here, so I may have talking about things you've already considered. But is your definition of dark matter the fact that your mass is small compared to the light?
So dark matter is just matter that's not luminous. So, I mean, dark matter is
by definition,
right.
that is it.
But people are trying to figure out what dark matter is. So we don't really have a good handle on what dark matter is. People are searching for it, and we know it's there from its gravitational effects. But you can't observe it directly. You just see it's indirect.
Because the light is small compared to the mass, we're calling it dark matter.
Well, in these galaxies, they're dark, what we call dark matter dominated. So the ones I showed you tonight, there's very little light because there's only a few stars. And then you know there's dark matter there because of the orbits of those stars. But then there are other clumps of dark matter out there where there's no stars in them at all. We just infer their presence from their gravitational pull. The clumping looks very similar in theory to that simulation I showed in the beginning with all the hundreds of little blue points around the Milky Way. But people have been searching for dark matter pretty strenuously and not finding a lot of it. So that's the theoretical prediction of how it clumps. How it actually clumps, we don't have a good handle on yet because it's very difficult to observe directly.
Yeah, there's a huge difference between the simulated ideas of it and what Tom can actually observe.
Right.
So it's really difficult.
Yeah, I mean, since we can't observe the clumps that have no stars, we really can't observe those directly. So what I'm looking at here are the ones that just formed a few stars, and that gives us gives credence to the theory that why the missing satellites are there. It would be great if we actually observe those hundreds of clumps that we don't have any stars in. So yeah.
For instance, how old are Andromeda and the Milky Way?
So the oldest stars in those galaxies go back to the Big Bang within the error bars, so back to 13.5 billion years old or so. So that was the image that's on the David Bowie album. That was the goal of that program, was to measure the range of ages in Andromeda out in its halo of stars. And so we found stars that were 13.5 billion years old, and we found stars that were just 1 billion years old, everything in between. And that's the case for the Milky Way, that's the case for Andromeda, that's the case for the satellite galaxies that we've known about. It's these ultra-faint dwarfs that only have ancient stars. Every other galaxy we've looked at has young stars, I mean young for an astronomer, significantly less than 10 billion years old, and old stars as well.
Right, and so just to amplify that, what you might have also been asking is that the structure of the Milky Way is believed to have formed around 10 billion years ago. Okay? The structure of the disk of the galaxy, etc. So some stars are as old as the universe, but the structure itself is hypothesized, not hypothesized, is believed to be about 10 billion years old.
Yeah, and we can see that by looking at higher redshift. So if you look at in the very distant universe, which is looking back in time, you can see most of the universe with smaller galaxies, and then they start clumping together and forming more massive galaxies as they merge. So, yeah.
There's some technical reason why we don't build these bigger telescopes now, bigger than, like you were describing, bigger than the James Webb?
Well, yeah, I mean, there's one technical reason. So, I mean, yeah. 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 Right here, I guess, yeah.
How many procedures is that to open that all up? Have they figured out how many procedures?
Yeah, I mean, commissioning on James Webb lasts 6 months. So it's a 6-month process.
Different
Steps?
steps.
I mean, hundreds and hundreds of steps, right? I mean, so there's a lot of steps, different things unfurling. The folks...
Will it be done in different stages of its travel?
Yeah, so it'll be deploying on its way to the Lagrange 2 point, right? So, and then we'll be monitoring it the whole time. And there's some things you don't want to do until the telescope is cooled significantly. It's cooling off on the way there, and there's a careful orchestration of events there as well, so you don't have like ices accumulating on the instruments and their optics and so forth. So it's a very careful choreographic series of events as it goes out to Lagrange 2. And then after the first 6 months is over, we start doing science. That's the plan. All the way in the back? Yeah, so we use it because that's a very good explanation. So the James Webb Space Telescope works primarily in the infrared at wavelengths longer than our eyes work, and a very good substance to work with for the reflectivity at those wavelengths is gold. Right.
Let's try the other way in the back.
Sure. Yeah, okay, way back there.
It's always so hard to see them.
Yeah.
Could you talk a little bit more about why the reionization of the universe actually does shut down star formation?
Sure, so the lights come on, so when the very first stars and galaxies form, you have these massive stars, and the universe gets flooded with ultraviolet light. So it's very, very energetic light, X-ray light as well, even higher energy light. And when it goes sweeping through the universe, and all this neutral gas gets energized and reionized. So basically, the electrons get stripped off the atoms. And so that's a very energetic process when the universe, very earlier on, is much, much hotter than it is today. Today, the temperature of the universe, the cosmic microwave background, is 2.7 Kelvin above, so it's 3 degrees above absolute zero. Back in the early universe, it was much, much hotter. And so what happens is this energy goes sweeping through the universe. You have these clumps of dark matter, which are like little gravitational wells. They have gas sitting there in the dark, with the dark matter. And then this energy comes sweeping through and sweeps the gas out of those clumps of dark matter. It doesn't do that for the really big clumps of dark matter. So the really big clumps of dark matter, they don't lose all their gas. And also because they have more gravity, they reaccumulate that gas and sweep it back up. But these small clumps of dark matter, the ones that don't really form stars, the gas is swept up and never comes back. And so they don't form stars then. It's just a clump of dark matter. They've been stripped of their gas. So how about right over here? Yeah. So to the right, you in the red shirt. Here you go. If I understand. Yeah, maybe you could repeat it one more time. I'm actually not sure.
I think she's asking, why do we get the globular structures in some galaxies and the disk structures in other galaxies?
So the dark matter is driving the large-scale structure of the universe. It's like I said, it's kind of like the scaffolding that all the gas and matter in the universe accretes along there. And then much more complex things happen on small scales, like the Andromeda Galaxy or the Milky Way. Basically, you have things that are spinning, and then they start to collapse perpendicular to the direction of spinning. It makes a disk. There's still a swarm of stars, kind of like a bee swarm around that. That's called the halo. So it's a very, very complex hydrodynamical process. I mean, I don't have a simulation on my computer, but basically you have a lot of interactions between the matter on the small scales of a galaxy. I mean, galaxy is small for our purposes here. On the large scale of the universe, you have these filamentary structure, these filaments of dark matter, where all the matter kind of collapses along those filaments. And where a couple filaments come together, you have a galaxy form there. So.
Okay, Tom, we've got a question from online.
Sure.
Are ancient stars metal poor because there hasn't been a lot of star recycling yet?
Yes. Well, an ancient star, if a star is ancient, if it was born in the early universe, it won't have many metals, period. Then if stars are born more recently, they could be born from pristine gas if they just happen to be in a lucky patch of the universe. But more often than not, because there have been multiple generations of stars, those stars have, the stars that have already blown up in supernova, they've polluted the gas. And then new generations of stars are born and they have many more metals in them. So, how about right here?
What's your or the community's favorite current hypothesis as to what dark matter actually is, or is there really no consensus at all?
Yeah, I mean, I don't have an opinion on it because I'm not a theorist, right? But people are still arguing about it until we can actually, measure it more directly. There's not, there's a lot of theories out there, right? So, yeah, right here.
Yes, the percentage of dark matter, dark energy, the current estimate?
So dark matter is around 20 to 25%. Dark energy is around 70% or something like that. And then there's just a few percent is baryonic matter, like what we're made out of and what stars are made out of. Yeah, right here.
So, do you have any ideas as to how gravity's relationship to dark matter is different? Like, why do the galaxies form around these dark matter clusters specifically?
Because most of the matter in the universe is dark, so they're the biggest source of gravity in the universe. So.
It's just because there's more. It's not like one particle of dark matter has a larger or lesser gravitational pull.
Not that we know of, and in fact, dark matter itself we don't really even know how much it interacts with normal matter, in fact. I mean, we see the effects of its gravity. You can see the motions of stars in the Milky Way are moving in a way that implies there's a lot more mass there than the mass of the stars we can see. So we know the dark matter is there. We know it has a gravitational effect on things. But other than that, we don't know a lot about it. We don't know how much it interacts with itself, how much it interacts with other matter.
Yeah, a figure to think about is about 85% of the mass of the gravity in the universe is dark matter. Okay, only 10 to 15% of it would be normal matter.
Yeah.
So, why was the Lagrange 2-point chosen and not one of the other Lagrange points?
Just because it's pretty accessible and stable. So this is a good place to put it out there. We've put other.
Repeat the question.
Oh, okay, sorry. Yeah. So the Lagrange point was chosen. The question was, why was the Lagrange 2-point chosen for JWST's orbit? We actually put a lot of satellites out there because it's a relatively stable point. It doesn't take a lot of fuel to keep a satellite in orbit around that Lagrange point, and it's fairly accessible compared to some of the other Lagrange points, which are on the other side of the sun and so forth. Yeah?
When the ultraviolet light comes by, and you said, I think you said the electrons are stripped off.
Mm-hmm.
Where do they go? You said they go away, but what happens to the massive?
Well, no, we go into space. I mean, they don't go swept away and forever, I'm saying, but the gas in a local sense becomes so hot that the protons and electrons separate. But it's not like they're going to different parts of the universe. They're all local, they're together. And
They're moving, and later they form back to the metal.
oh, well, okay, there's a couple different things going on there. So the gas gets energized by the stars coming on, so it becomes ionized. And then also it basically boils out of the gravitational wells of these dark matter clumps. So the escape velocity basically becomes such that it escapes these dark matter clumps. If the dark matter clump is large enough, the gas will fall back into the gravitational well and continue forming stars, which is what most galaxies do. But if it's not, the gas just goes out into the intergalactic medium between the galaxies. So there is a lot of gas out there. I mean, in one of the press releases Frank talked about, people even look for galaxies by looking for neutral gas and so forth. So there's gas between the galaxies and between the stars as well.
So when you say it goes away, or were you talking about formation, or
It's no longer in those dark matter clumps. It gets swept out in between the clumps. Yeah.
You said the major problem with the 16-meter satellite would be monetary issues.
Yeah.
How expensive would it be exactly?
I have no idea off the top of my head. I mean, some of these things, there's an economy of scale that, that people are trying to leverage when they look at these future missions, but it would be very expensive. I'm not saying it would be technologically trivial either. We would have to work very hard on it as well. It's not like it would be a piece of cake, but it's within the grasp of today's technology, if the money was there. But it would be a lot more expensive than James Webb or Hubble.
What is Webb costing?
$8 billion.
Okay, another question from online. Would a 16-meter mirror telescope be able to directly image low-mass worlds such as Earth or Mars?
Yeah, that's the goal. I mean, it depends on how well separated they are from their host star, but if they were separated enough, then that'd be the goal, to see habitable worlds with such a telescope, to directly image them. Yeah.
We don't believe that reionization affected dark matter?
As far as we know, we don't think, I mean, dark matter, again, we don't know how much dark matter interacts with normal matter and energy and so forth. So it has a gravitational effect. Other than that, I don't know a lot about dark matter. There's a lot of theories about it, but no. Mostly the reionization, when you're talking about reionization, you're talking about the baryonic matter.
Okay, this gentleman over here has had his hand up.
Sure.
How does black holes interact with the dark matter?
So the question is, how do black holes interact with dark matter? Black holes are a form of dark matter. We don't think they make up a large part of the budget of dark matter, but they interact gravitationally with dark matter as well. So dark matter can interact with a black hole gravitationally. Other than that, we don't know how dark matter interacts with ordinary matter.
Yeah, we actually had a discussion about dark matter online during your talk.
Okay.
People wanting to know, well, what is dark matter? And I said, if I knew that, I'd be on track for a Nobel Prize.
Yes, it's true. Right, okay.
I think.
You said that the dark matter, there's more mass in the dark matter than there is.
Yep.
So why do we call it the scaffolding? Typically, scaffolding is less than that, which is a torus. So why is it affecting us rather than our matter affecting the dark matter?
Well, I mean, I could use another analogy, but to me, the dark matter is traced throughout the universe in these filaments, and then that thin layer of gas and the leftover matter, the kind of matter we're made of, kind of falls gravitationally on top of that, and where it collapses together due to gravity, it starts forming stars. So to me, it's the structure upon which everything else is built. When you see the large-scale structure of the universe, it's defined by dark matter, the same way that the scaffolding of a building defines the structure of a building. But I mean, there might be better analogies. But yeah, go ahead.
So I have a question more on the computational side of this image analysis and feature detection. So in trying to identify signal-to-noise differentials, how confident are you in terms of the deduction algorithms to reduce what is really a feature versus an artifact?
All right, try and summarize that question for the online
Yeah, so
audience.
for the online folks, how confident we are in the algorithms that allow us to reduce the data, basically. So pretty confident, because we came at this a couple different ways. As I showed in the talk, we have comparison populations that are very, very well studied. So we use this camera, this very, very sensitive camera in Hubble. We measure the brightnesses and the colors of the stars. And then we use the same exact camera and filters to measure a well-studied object, and that's our control. So in this case, I showed M92. We've actually used it for loads of studies on Hubble, but M92 is the best comparison here. So you can do an apples-to-apples comparison where a lot of the systematics you might be worried about just drop by the wayside, because you're doing the same exact thing with both M92 and these galaxies. And then we also come at it from a different angle. We take the theory of how stars evolve, that pattern they trace out in the diagram, and we calibrate those theoretical models to the data that we've taken with this camera over and over and over again. So that's another way of doing it. So no, we're pretty confident. And then measuring the stars, the signal noise to get this accuracy in the ages, we got a signal noise of 100, since you mentioned signal noise. So the signal noise ratio is 100. So it's very, very, 1% photometry.
And let me just say, the folks in this building are brilliant. I'm not an observer, okay? You guys are absolutely brilliant at characterizing all of the artifacts that could be possible in Hubble images, okay? They've had 25 years to work at this and really understand all the stuff, and they do amazing stuff at being able to really pull out what's signal and what's noise out of these out of the data sets.
And a lot of the sources of systematic error, like for example, this object right here that I'm moving to, well, I probably blew past it just now, but M92 is a very crowded star field, so it gets a little noisier in the data. Well, I'll show you this. This is a very sparse star field, so it's pretty easy to measure here, let me show you again here. That's a very sparse image. And if I zoom in on it here, it's pretty easy to measure the brightness of this star, and so forth. because they're not stepping on top of each other. You know, it's just a nice, well-isolated star. So really, we tried to make this measurement a turkey shoot. We did very long exposures, left the shutter open for 16 orbits, really get accurate measurements of each of these stars. And they're not crowding on top of each other or anything. So unlike M92, where it's a little harder because the stars are so crowded. Yeah?
What causes the dark matter to form into film?
Gravity.
From what?
Itself, so self-gravity. It has a gravitational influence on the rest of the dark matter. So it just collapses on itself. Yeah,
talk to Albert Einstein, okay? All right, any last questions? Back corner up there.
Yeah, do you foresee any privatization of any of these larger telescopes coming about, like we've seen with privatization of space launches and things like that?
I mean, it could happen if Elon Musk wants to, say, hey, I'll launch a satellite on the SpaceX for you guys or whatever. You know, it's possible. Right now, the discussions that people are talking about, they're all talking about NASA launches. But it could happen in partnership with private industry. Who knows? It's possible. Yeah.
Can you replay the unfurling video?
The what? Which
I'd
video?
like to see the JWST video again.
Oh, the deployment video? Yeah. Sure. Yeah, there's a better one available on the web now since I put that one in the slide that is a little more exciting. This one is almost like, scale equals 1 time. It almost happens. It almost takes like 6 months to watch it. But let me blow through this. This is why I don't put transitions in my slides most of the time, because I hate waiting for those.
Okay, well, while you play the video one
Yeah.
more time, here's a question from online. Is it possible that there could be planets orbiting the stars in these small galaxies? These galaxies were formed 13 billion years ago. They're low metallicity.
So probably not.
Are we going to find planets around them?
So astronomers, when they look for planets around stars, planets are very abundant, as we're finding out, that we find them around stars all over the place, on nearby stars. But as Frank was just saying, these stars were born in clouds of gas that were very pristine, not a lot of material for building planets. So there's not a lot of likelihood here that there will be planets around the stars in these ultra-faint dwarf galaxies. The analogy I can make is that Hubble did a very, very thorough search for planets in a globular cluster. I guess it was around 15 years ago now, 47 Tuc, which is not even as metal poor as these ultra-faint dwarf galaxies. It's a little more metallicity than 10% solar. So it's not like 1% or 1,000th of solar like these. And they didn't find any planets around those stars. So really, if you want to look for planets, you look for stars that are closer in metallicity to the sun, because those are more likely to be born from material with a lot of enriched gas and so forth around, where you have the building blocks of planets as well. So there's probably not a lot of planets in these galaxies, in these ultra-faint dwarf galaxies.
Okay, well, thank you all for coming tonight. If you have any last questions, come up and see if we can chat. Next month, Bill Blair will be talking about stellar populations in Messier 83. Remember that next month you must approach from the south, not from the north. And let us give Tom another warm round of applause. You didn't go too fast.
The data looks too good. When I got out of graduate school, went to Corning Research, we had to give a monthly talk, and we had in those days an optical